today. So I actually used the first few minutes of this workshop to make the last couple of slides of this presentation. But then I hope so it's not very comprehensive analysis of the results I have. But I hope it's going to be interesting anyway. And if it only was because it's a little bit different from the protein story. So I work for this place called Research Center for Pharmaceutical Engineering, which is another public-private outfit in Graz in Austria. And we are primarily involved with formulation development rather than drug design. Meaning we have a drug, we know it works, but then we have to make this into a pill, for example, or a parental formulation, whatever. We have to formulate it so that it can actually be applied by a human and do its job. So one of the no. Oh, there we go. Yeah, that's fine. So this is yes. Okay. How do I get back? It works now. So sorry. So okay. So one of the recurrent issues that's getting more and more prevalent these days is barely soluble drug candidates. Actually, one of the culprits for having all these barely soluble drugs is you guys who make all these drugs from virtual screening, which are typically poorly soluble. And so one idea to cope with that is to make what they call amorphous dispersions. This is based on the fact that if you have an API molecule, a drug, in this crystalline form, that's poorly soluble, then you can increase solubility by using the amorphous form or state of this API. And this amorphous API needs to be stabilized in some way or the other, because typically, the amorphous form is less stable than the crystalline form. And if you wait some time, it's gonna crystallize and you lose your solubility edge. So the idea is you embed your amorphous crystal that you can prepare, your amorphous compound that you can compare in various ways in a matrix made of synthetic organic polymers. And then it's simply better soluble many times. The problem here is that these formulations are typically they are less stable than the crystalline form, and then becoming crystalline again is only a matter of time. And so this time actually, how long it takes to become crystalline again is a limiting factor there, and people are working on this actively. And whether it's stable for long enough is basically a question of course, process parameters, how you actually make it, but also of the specific API excipient combination. The excipient is basically the polymer here, and you can use a range of different polymers to make these formulations. Now, and we are basically what we try to do is to try to understand and ideally predict the stability of different amorphous solid dispersions based on different polymers for a given API in silico. Good. So that's basically the physics. You start here. We don't have a point to do it. So, okay, whatever. So we start basically at this amorphous solid dispersion. It's basically a random mixture of API compounds with some polymer. And as I said, the free energy minimum is typically at the crystal side of things. Yeah? So the question is, how long does it take to get there? And there's various free energy barriers in between. And here we basically concentrate only on this first step, how to get from the homogeneous amorphous solid dispersion to a phase separated system, or that's very nicely. So this first step is what we consider. And now the question is actually, I've said all that, I guess. But now the question is basically, this has again this is basically a glass, and I mean glass. The science of glass is old by now, and there's a lot of theories out there, but it's still very unresolved actually, and it's interesting. And the physicists have been working on that for a long time. Recently, the pharmacists have started to work on that too, because that's what the system is, a glass. And there's various factors that stabilize these kind of formulations. And the two factors that are most important for stability are basically kinetic and energetic factors. Basically this barrier here or this energy difference here, and we don't really know which one is more relevant in this aspect. So we took a model system this year basically, which these are literature data. We didn't do that. We just took that from the literature. These are 3 different APIs, drug compounds, and we combined that with 4 different polymers and try to see if we can predict the relative stabilities. Yeah? And the stabilities are actually here. These red bars are the measure of the stability of the amorphous solid dispersion, meaning the higher the bar, the higher the so-called amorphicity index, the more stable the mixture is between the polymer and the API, the amorphous mixture. And the lower it is, the quicker it's gonna become crystalline again. Yeah. And there's so we took these 4 different polymers, yeah, and mixed it with each polymer in silico, and try to see what kind of descriptors correlate with this stability. So these are the polymers. These are commonly used polymers in pharmaceutical formulation development. And yeah, the models. I mean, what people in the literature have done, mostly the pharmacists, is that they did MD simulations, calculate the energetic interactions between the polymer and the API, and they conclude that if this is a good interaction, if it's favorable energy, then this is going to be a good match and it's going to be stable. But the question is whether this is really so simple. So the methodology we use, I mean, that's pretty straightforward. MD simulations, you all know how that works. And I spare the details now. We can talk about that later if you are interested. So, and the caveats, we only consider this initial step of phase formation. We assume that all compounds are neutral and stay so, which is probably a decent assumption. And the other assumption, we calculate energies, like mixing energies between polymer and API. Yeah? And of course, interesting would be to know the mixing free energy, which is very difficult to calculate for this kind of systems, because if you've got a condensed system and calculating free energies there is really quite a bit harder than doing in aqueous solution. So we just do with this here, and in this case it's probably a decent approximation because there's no water anyway, and water is typically the entropic liability, if you will. And then we calculate these different descriptors. I'll show you what we calculate. We calculate the free volume of these polymers, which is typically a measure of their stability to some extent, or the mobility in there. Then we calculate the variation in the number of hydrogen bonding between the pure polymer and the pure API versus the mixture of the two. And then we calculate also the mixing energies, basically, to go from here to there. And we calculate the diffusion coefficient, which is basically a measure for the kinetic effect. Yeah? Fair enough. So the first results that we saw is that the change in hydrogen bonds and the change in the Coulomb contribution to the binding energies or mixing energies correlates very well, as does the mixing volume and the van der Waals contribution to the mixing energies, which was to be expected. I won't discuss this here any long. So we concentrate on these two descriptors: the Coulomb contribution to the mixing energies, and the mobility, which is basically the diffusion coefficients of these API molecules in the polymer matrix. Yeah? So first candidate is this flufenamic acid. This has a strong donor here, so we would assume it to interact favorably with polymers that only have acceptors but no donors. And what we see is is this basically here? So yes, this is this amorphicity index. So the higher is, the more stable the mixture is, and we see, and that correlates reasonably well. You see that basically the two compounds or the two polymers that give a more stable mixture also have the more favorable mixing energies. So this is, well, I mean, it's not a perfect correlation, of course, but considering that these were fairly simple calculations and we didn't optimize any force fields or whatnot, this is a decent correlation. The mobility on the other hand side doesn't correlate at all. So this basically confirms what in this original paper that was published with this data was speculated, namely that these basically the energetic interactions between polymer and API played a decisive role in determining the stability. This is a different picture with average amorphicity indices, as they call it, rather than specific, but I can't go into that now. It's pretty much the same thing. Anyway, so the next compound, here we've got a relatively weak donor and an intermediate acceptor. We can assume that this perhaps might prefer polymers that have donor functionalities, like this polyacrylic acid or polysulfonic acid. And it's relatively flexible compared to the other two. So what we see is we see no correlation whatsoever, actually. So this is something I'm still struggling with at the moment. We might miss the entropic contribution, actually. I'm not sure. Actually, I don't believe that really. Probably it's got something to do with the fact that it probably crystallizes and that the rate limiting step is somewhere else. And the third compound that we looked at was this Phenacetin, which is similar to the previous one, actually. It's a little bit smaller and more rigid. And that's again a weak donor and an intermediate acceptor, and we might assume that it prefers these sort of polymers due to the hydrogen bonding interactions. What we see actually is that the energetic factors don't correlate at all with stability. What does, and you might argue that this correlation sucks. It's really poor correlation. It's only 4 compounds, so this is no statistics. But I should stress that what we are looking here is what we want to do here is not make a predictive QSPR model or anything like that. We want to understand the physics, and for that this is good enough, I guess. So we've got basically one compound that's much less stable than all these 3 others here, and this has a much higher mobility in the matrix, which means that it's faster in getting to the equilibrium structure, and the equilibrium structure is the crystal, or actually the phase separated state, and therefore this guy here is less stable. So this makes sense. So yeah, the convergence. So this ties in a little bit with the topic that we're talking about here, basically fast computing. Yeah, namely, so one issue that we had here, of course. So there's all these methods up there that can be used to accelerate exploration of phase space, energetic space again, free energy surfaces, and this is fine. Unfortunately, there's no such thing, no such trick to accelerate the calculation of diffusion coefficients, and that's the reason why this took, actually, all the calculations I showed you there took more than a year on a small cluster we have in-house, exclusively used by me. So this is fairly expensive in terms of calculation of computational time that's required. And this is what you see here. Basically, this is the convergence of the diffusion coefficients, and it's freakingly slow. As you see, this is 1 microsecond here, and it's still not totally converged, but we get a reasonable difference here at this point. So we should probably carry on for another microsecond or so. Yeah, and what's the physics in that? How do we explain that? It's probably very simple, actually. If you look at the 3 compounds, this Flufenamic acid, the first one we discussed, where we see a correlation between mixing energies and stability, we see that these mixing energies actually cover a quite large range, and the diffusivities cover a relatively smaller range compared to the error bars again. Yeah. Well, for the other compounds where we found that the diffusion, the mobility is rate limiting, we see basically the opposite. We see that we have a relatively small range of energies for the four different polymers, but a comparatively large range of diffusivities. But this is good in a way, because this would enable us maybe in the long run, if you do more such calculations, to define some kind of thresholds that should explain whether a certain compound at some point is diffusion limited, or the stability is diffusion limited, or energetically limited. Yeah, and then these are the conclusions. We basically we looked at 3 different compounds. They showed 3 different trends with respect to stabilities with different polymers, and in 2 of these cases we can explain that. In the 3rd case, we're not sure yet. The important conclusion in any case is that there's no simple one physical descriptor that can explain the stability of these systems on its own. Yeah, I believe. Yeah, I'm done. Thank you.